Okay, you should have out your notes for lecture 52, hypothesis testing for the difference of means, unpaired data. All right, so what we want to do is we want to, I say here, we're going to consider the difference in means between two sets of data or two populations where there is not a natural pairing between the populations. So we're starting with two populations. We want to compare the means between them. So if you think about it, before we were analyzing a before and after population, right? And we took the difference between whatever we were measuring, weight or whatever, between an individual before and after, and that gave us a difference. And so we had one data set, just the data set of differences, because we had a natural pairing here, so we knew what to subtract from what. But now we don't have that. Now we just have two completely different populations. And so we can't pair them and do differences individually, but we can look at the means separately and then look at the difference of the means, and that's what we want to do here. So instead of analyzing the mean of the set of differences, we're going to analyze the difference of the means of two different populations. Our test statistic is more complicated, but it's still a random variable, still a t-random variable. All right, so we have two populations of data, P1 and P2, with respective means mu1 and mu2. And we're testing the claim whether the difference between these two means is some value, and usually we'll have that value be 0. So in other words, we're saying that the means are equal. Saying that the means are equal is saying, mu1 equals mu2, right? But that's the same thing if I subtract one or the other from both sides. That's the same thing as saying mu1 minus mu2 is 0. That's the same as that, right? Or I could switch it around and say mu2 minus mu1 is 0, right? So to get a number on one side, we subtract. So we're not just talking about the two being equal to each other, but we're saying their difference is 0. And I think this is the one that I end up using in what follows. Mu2 minus mu1 equals 0. So that's usually what, essentially what the null hypothesis is going to be. You'll see coming up. In fact, I guess I'm ready for that. I hit my button here, so we're ready to look at the null hypothesis. So the null hypothesis is going to be, let's see, right here, null hypothesis is mu2 minus mu1 equals 0. And so the alternative will be, one would be mu2 minus mu1 is greater than 0, right? So that's a right-tailed test. So we know over here we'll still have mu2 minus mu1 equals 0. And for the left-tailed test, the alternate hypothesis would be mu2 minus mu1 is less than 0. And of course, for a two-tailed test, mu2 minus mu1 equals 0 is the null all the way across, and the alternative here is mu2 minus mu1 does not equal 0. All right, so that's what the hypothesis test will be, and all you need to do really is understand what the test statistic is. If you understand what the test statistic is, you can pretty much just go from there. And I say here, we take a sample of size N1 from the population P1, a sample of size N2 from P2, so you may not even be taking the same size samples. That's okay. And we compute the respective sample means and sample standard deviations. So from first sample from population 1, we compute x1 bar, the sample mean, and s1, the sample standard deviation. From the second population, we compute x2 bar, the sample mean, and s2, the sample standard deviation. And because we are dealing with the combining of two samples from the two different populations, the test statistic is a little more complicated. So let me write it here. Test statistic. It is the kind of the representative of the difference of the means will be the difference of the sample means. So I will have x2 bar minus x1 bar minus what we think that difference should be in population, and we're saying that we think it's 0, right? We're going to say that that's what our null hypothesis is, right? Here, here, and here. So I'm minus 0, so I don't have to put anything, divided by the square root of, and it is the first sample standard deviation squared divided by the first sample size plus the second sample standard deviation squared divided by the second sample size, all right? And this is a t random variable. And then I say below it has what degrees of freedom? Degrees of freedom equal the lesser, the smaller of the first sample size minus 1 or the second sample size minus 1. Excuse me. Okay, so once you know that, that's about all you need to do, and you should be able to work problems. You should be able to do some hypothesis testing. We'll do a few examples here, but let me just say, where does this sort of thing arise? Well, the answer is whenever we wish to compare two populations, which we've actually been doing that all along. And so, for example, go back to the tomato plant example. We wanted to test whether our fertilizer increased the yield of tomatoes per plant. We started out knowing that untreated tomato plants had a yield of 12 pounds per plant. We then took a sample of plants and treated it with fertilizer and measured the new yield. The fertilized sample was like a sample from a fertilized population. So we really were comparing the two population means, the mean of 12 pounds per plant from the untreated population with the mean from the treated population from which we had the sample. All right? But suppose we didn't know what the mean yield was for the untreated plants. All right? We didn't know it was 12 pounds per plant. We would need to take a sample from that untreated population as well. And then we would be in our situation here where we have two means, mu1 and mu2. And we want to compare from two samples, one from the treated population and one from the untreated population. So let's do an example here. And I rub this out quickly. So you can read the example I have there and maybe get started on it. Get all this rubbed out. Okay, so let's suppose we wish to test whether our fertilizer causes an increase in the mean yield per plant in pounds of tomatoes. And we don't know what it currently is without the fertilizer, all right? So we don't know that it's 12 pounds or whatever. So we randomly select a set of 40 tomato plants that we will not treat with the fertilizer, and 50 plants we will treat with the fertilizer. We allow the plants to grow the prescribed length of time after which we measure the yield from each plant. And let's see here. You get past this. So we have two populations. One is all the yields from the untreated plants, and that mean we'll say is mu1, and the other is all the yields from the treated plants. And that mean pounds per of tomatoes per plant is mu2. Okay, and I guess I say here in the untreated okay, we want to know, is mu2 greater than mu1, right? That's what we're after here, is the mean from the treated population greater than the mean from the untreated? If so, that would say that we should be applying that fertilizer. All right, in the untreated sample, we find a mean of 12.2 pounds per plant, that's the sample mean, and a standard deviation, sample standard deviation of 2.8 pounds. In the sample we treated with the fertilizer, we find a mean of 13.9 pounds, a little bigger, and a sample standard deviation of 3.1 pounds. Does it look like our fertilizer is effective in increasing the mean yield per plant? All right, well, we want to know, is mu2 bigger than mu1? So what is the null hypothesis? The null hypothesis, well, as always, the null we're saying is mu2 minus mu1 equals 0, right? So the treatment had no effect. It was null, okay? The alternative hypothesis, the one that we're hoping, is that mu2 is greater than mu1, which means that mu2 minus mu1 must be greater than 0, so it's right-tailed. Okay, let's do, I think I say here, our test statistic, and I put it up there, so I think I have room to do it. The test statistic is, well, I know, excuse me, it's x2 bar minus x1 bar over the square root of s1 squared over n1 plus s2 squared over n2, and that's equal to, let's see, I have the sample mean from the fertilized group, the treated group, was 13.9 pounds. The sample mean from the unfertilized was 12.2 pounds, divided by the square root of the sample standard deviation from the untreated or unfertilized group was 2.8. So I have 2.8 squared over that sample size, which was 40, plus, and then it was 3.1 was the sample standard deviation for the fertilized group, and that's over 50. We compute all of that, and we get 2.728482848, et cetera, et cetera, et cetera, right? And what's the degrees of freedom? Degrees of freedom is, well, it's there's 40 minus 1 and there's 50 minus 1. That's 39 and that's 49. So it's that one, right? We use the lesser of the two. So if you go in the table, in a table, you find, so in table of, with the degrees of freedom being 39, what I find is that the critical value, T.005, is 2.708. All right, so that's smaller than that is, right? Now, I'm not, excuse me, I'm trying to get away from maybe drawing the picture every time, but you should think of what that looks like. Let me draw it this time at least. So here we are with our T random variable, and here is the T.005, right? It's 2.708, and a little bit out here farther is our our test statistic. Okay, so we would be out in the rejection region if we were using 0.005, which is 0.5% as our significance, right? I didn't give you a significance. We're kind of getting away sometimes, at least, from always giving a significance because we want to interpret things correctly. And the way that I would interpret this is I would say that the p-value then, remember what the p-value is, it's the tail probability that goes with your test statistic. The p-value is less than 0.005. P is less than 0.005 because, back here I have 0.005 area, right? So if I've gone beyond that with my test statistic, it's less than that. So I would say, so reject H naught. All right, so what's our conclusion? I would say here's our conclusion. With P less than 0.005, we have sufficient evidence. Try not to squeak so much. We have sufficient evidence. Let me see if this other marker won't squeak as much. Try the same color, but I think it's a little newer. We have sufficient evidence to reject the claim. Not much different. To reject the claim that the means are the same, that the mean yield of tomatoes per plant, the mean yields are the same. It appears the fertilizer increases mean yield per plant. All right, pretty easy, right? All you need to do is you need to understand the setup, you need to understand the null and alternative hypotheses. Then you need to know how to calculate the test statistic, and you need to know what kind of random variable it is, T with that degrees of freedom. Then everything else goes through as before. So you're just learning a couple of new things here, and they're just like what you've learned before, and you can do this whole new, have this whole new way of approaching things. So let me do another example. Let me just say, let me just say that, yeah, okay, you can read the top of, like, so my notes is top of the next page, some important terminology I give you. So let me rub this out while you read that. And then you can go on and read the next example. Right? But the thing to understand is that in a situation like this, and this is really where difference of means is used a lot, you're testing whether something has some effect, right? A fertilizer or a cancer drug or whatever. So you have a group of individuals that you perform the fertilization on or give the drug to or whatever, the group that you treat, that's called the treatment group. All right? The group that you don't treat, that's called the control group. Control group is probably something you've heard about before. Well, here's where it comes in. All right, so the tomatoes we fertilized, that was the treatment group. The tomatoes we didn't fertilize, that was the control group. And of course, a lot's going on here when you design the experiment. You have to be sure that you keep everything else the same. You know, you water them the same, you give them the same amount of sun, all that sort of thing. And we'll talk about those things later on in the course. But the idea is you vary one thing, if possible, between the control group and the treatment group, and that's the thing you're trying to test, fertilizer or a new drug or whatever, depending on what you're doing. Okay, next example. You were assigned to test whether mop top, high times new hair growth elixir for men, causes men to lose weight. You form a control group of 60 men and a treatment group of 100 men. The treatment group receives a daily dose of mop top as recommended on the label, and the control group receives a placebo with the same taste and texture as mop top, keeping everything the same as much as possible, except the one thing that you're trying to test, right? And let's see, where am I? Let me back up here. Okay, so here we go. So that's my example. Sorry, I got to go through all this again to get to where we are. Boom. Reject or fail to reject. I guess I didn't write this up there, but okay. Okay, now the next example. So we've been reading that. So we got 60 men in the treatment group and 100 men, or 60 men in the control group and 100 in the treatment. The treatment group receives a daily dose of mop top. The control group receives a placebo, the same taste and texture. After 6 weeks, each man in each group is weighed, and the results are, so let's see, I have, the control group is, the mean weight is 182.2 pounds, and the sample standard deviation is 21.6. And the treatment group, the mean weight is 174.8 pounds, and the sample standard deviation is 32 pounds. Based on this, should high times be concerned that mop top causes weight loss? Okay, to answer that, we have to construct what the hypothesis test is going to be. So we got to first come up with our null and alternative hypotheses. The null hypothesis is, of course, that let's make it clear that X1 is the control group. So mu1, that's the population weight without mop top. Right? And mu2 is the pop weight, the mean pop weight, the mean population weight with mop top. Okay, so the null hypothesis, of course, as always, is mu2 minus mu1 equals 0. The alternative this time is I want to see if there is a weight loss, right? So if mu2 is the mean where they're using it, then I would expect, if there's a weight loss, I would expect this mean to be smaller than that mean, so less than 0, right? And so we have a left-tailed test. Okay, let's do the test statistic and analysis. I think I have right here. The test statistics, let me rub this out. We have that. Once again, we do x2 minus x1 bar each over, oh, sorry, I'm writing up in my words there. I'll go down below here, yeah, okay. x2 bar minus x1 bar divided by the square root of s1 squared over n1 plus s2 squared over n2. And that's equal to x2 bar is 174.8 minus x1 bar is 182.2 divided by the square root of S1 is 21.6, so it's 21.6 squared over, and that was the control group, and there were 60 of them, plus, and then the sample standard deviation for the treatment group was 32.0, so that's squared over, there were 100 of them. So you do all that calculation, and you come out to, what, negative 1.7434, ... Okay, something like that. All right, what's the degrees of freedom? Degrees of freedom is, let's see, we have 60 minus 1 is 59. We have 100 minus 1 is 99. That's not it. It's the smaller of the two, right? But most tables don't go to that much detail, so we'll use 60. We'll go up to 60 because that's in most tables. And if you look, what you find is this. You find that T of what do I have? T of 0.05 is 1.671, and T of 0.025 equals 2.00. Okay, now it's a left-tailed test, and remember the critical values we're given are always given positive, so it's like they're assuming it's a right-tailed test, but everything is symmetric. So really what I'm after here is the negative of that, which is negative, and the negative of that, which is negative. Okay, what I see is that, my test statistic lies in between these two, right? So again, here I am drawing the bell of the T curve again. What I have here is oops, sorry, it's got to be over here. Oh, that's okay. All right, so I have here T.05, and I have here T.025, right? And it's in here where my test statistic lies. Okay, so I would reject at the 5% significance level. I would fail to reject at the 2.5% significance level, right? So what I would say here is, well, the p-value is obviously between 0.05 and 0.025. The tail area for here is 0.05, for here is 0.025, and the test statistic is in between, so the p-value is somewhere in between there. But it's less than 0.05, so let's see, am I ready to ask for a conclusion here? What do I have? Do we reject or fail to reject? Okay, do we reject or fail to reject? I would say with p less than 0.05, we should reject H naught, and I say a little bit here, don't I? Let's see. Okay. No, I don't. I guess I do here in the conclusion. Let me write in the conclusion. Why am I rejecting? Why am I saying, well, we're taking the 5% significance level rather than the 2.5% significance level? I say this. P-value is between 0.025 and 0.05. Since this is a medical test, we want to be on the safe side, right? So we want to set our significance fairly high. We set our significance fairly high. Let's just say 5%, which isn't really all that high, but I mean, it's higher than the 2.5%. So I'm going to say that we should probably reject based on that. So we conclude there is sufficient evidence that mop top causes weight loss. All right, so hey, maybe it should become a weight loss drug. I don't know. All right, well, so I'm hoping that you are seeing that this is a brand new thing, but it's really not that different than what you've already been doing. Once you can interpret correctly things so that you get the null and alternative hypothesis set up correctly, and then you compute the test statistic and you see which, t-random variable it is, everything goes through as before, right? So it just shouldn't be that surprising to you. And I'm trying also, based on stuff we've been talking about, I've talked about in recent lectures, I'm trying also to incorporate that in here, and that I'm not always saying, okay, here's the significance level, let's test it. I'm kind of not giving a significance level, and then you have to do a little interpretation. You have to kind of think what's going on. You look at the p-value, and of course, if we had used technology on this, we would have gotten the p-value calculated perfectly. But we knew it was less than 0.05, and if we were deciding kind of that on our own, that because we want to be sure to reject something if we think it might be causing a problem, we set our significance level, we don't set it to be 0.001 or something like that, right? We set it to be, in this case, we just kind of decided 0.05, so we went below that, so we reject. Okay, I guess I got just a few more points to make here. So let's see. So final conclusion, which I just wrote, all right. So some final points, and I think you have a place to write these. If the standard deviations for each of the treatment and control populations is known, so standard deviation for each is known. In other words, if I just happen to know what the standard deviation is for the control population and the standard deviation is for the treated population, these can be used in place of the sample standard deviations, and then you get a z random variable. Everything else carries through. It's just z, which is a little easier than t, right? But that scenario is highly unlikely. I'm not going to do an example. Next point. If neither standard deviation is known, as we've been doing, but we have some additional information, is known maybe that they are the same, or strongly believe that they're the same, then it actually can simplify the computation and produce a somewhat better result. Again, it's not a likely thing to happen, so we won't explore that here either. How would you know that, hey, the two populations have the same standard deviation? Don't know what it is, but it's the same. That just is not that likely to happen, so I'm not worried about it here. The actual degrees of freedom calculation is more complicated than what we are using here, but it won't likely lead to a much different result than our way of calculating it here, so we won't worry about that either. If you use technology, it'll automatically compute it correctly. But what we got is pretty good, for what we're doing, looking things up in tables and such. And I think finally, it is not necessary that the null hypothesis be that mu2 minus mu1 equals 0. It could be that we want to test whether that difference is some non-zero value. Is the treated group, 5 units more than the untreated group or something like that? Instead of 0, instead of the difference being 0, it could be 5, for example. So we can do that. The only difference is that our test statistic now becomes what? Okay, so the test stat is it's x2 bar minus x1 bar over the square root of s1 squared over n1 plus s2 squared over n2. If you say that enough times, it becomes easy to do. But now we have to extend it here and say, before I told you that it's like if we're thinking of that difference as being 0, we're subtracting 0 here, so we don't have to write anything, so this is what we have. But if we're thinking of it might be non-zero, then we got to do this, whatever we're saying that we think it is. So we subtract away whatever that difference is. Everything else goes through. All right, so everything else goes through as before. You would just do that difference. So I'm not going to look at an example like that because, number one, almost always you're testing whether the means are the same or not. So that is 0, and you don't worry about it. Number 2, it's just not that much harder. We could do 1, but you just be sticking up a difference here, whatever you think it is, 5 or 20,000 or whatever, and then you just work everything through as before. I guess the other thing, I didn't write this down, the other thing is that if you look, a lot of textbooks might have the difference switched around. They're doing x1 bar minus x2 bar instead of this way. It absolutely does not matter which way you do it. It's just that if I'm doing x2 bar minus x1 bar and I have a right-tailed test, if you do x1 bar minus x2 bar, you're going to have a left-tailed test, right? And it all comes down to just looking at what the problem tells you and deciding which way I subtract it. Does that mean it's a right-tailed or a left-tailed? Okay, so it really doesn't matter which way we go. I just do, the bigger index minus the smaller index. Just that's a way I've organized it in my head, but it absolutely doesn't matter. Okay, we'll stop there.